All right, welcome. If you're a new water treatment operator, you are in exactly the right place. We're about to break down one of your most important tools, the Langelier Saturation Index, or as you'll hear it called, the LSI. This is your practical guide to what it is, why it's so critical, and of course, how you actually use it. So, here's how we're going to tackle this. First, we'll talk about the basic problem with water that makes the LSI so necessary in the first place. Then, we'll properly introduce the index itself before we decode the formula behind it. After that, we're going to roll up our sleeves and do a real calculation together, step by step. And finally, we'll figure out what that number you get actually tells you about your water.
Okay, let's just dive right in. You've probably heard that water is the universal solvent. And that sounds great, but what it really means for us is that if water is out of balance, it will try to fix itself. And sometimes that fix means it starts dissolving your pipes or clogging up all your equipment.
And that brings us to the big question that every single water operator has to answer. What is the personality of your water? Is it aggressive and corrosive, literally eating away at your infrastructure? Or is it oversaturated and scale forming, leaving behind mineral deposits that can choke the whole system?
Think of it this way. Corrosive water is hungry. It's looking for minerals, and it's happy to get them by leaching calcium right out of your pipes. On the flip side, scale-forming water is full. It's totally oversaturated, so it starts dropping its extra minerals everywhere, which builds up and creates blockages. And trust me, both of these are huge problems that lead to very expensive failures.
So how in the world can you tell which way your water is leaning before all that damage is done? Well, that's exactly where our key predictive tool comes in, the Langelier Saturation Index.
Put simply, the LSI is basically a gauge. It's a number we calculate that predicts whether your water is more likely to create scale by precipitating calcium carbonate or cause corrosion by dissolving it. It's like a snapshot that tells you what your water wants to do next.
To really get this idea of saturation, let's use an analogy we all know. Picture this. You're making a sweet drink. You take a spoonful of sugar, you stir it in, and poof, it disappears, right? It just dissolves.
But what happens if you keep adding more and more and more sugar? Eventually, you get to a point where it doesn't matter how much you stir. That sugar is just going to sit at the bottom of the glass. The water has hit its saturation limit. It literally cannot hold any more.
Okay, now just swap out the word sugar for calcium carbonate. That is exactly what the LSI is measuring. It tells us how close the water is to being full of calcium. Is it undersaturated and hungry for more, or is it oversaturated and full? So what's the perfect score? What are we aiming for? It's 0, a flat 0.00. That means the water is perfectly balanced. It's holding just the right amount of calcium carbonate, so it doesn't want to dissolve anything or deposit anything. It's in equilibrium, which is exactly where water wants to be.
So how do we actually get to that number? Let's look under the hood at the blueprint for this calculation. And don't worry, it might look a little intimidating at first, but we are going to break it down piece by piece. The main formula is actually really simple. The LSI is just the actual pH of your water, the one you measure, minus a calculated value we call the pH of saturation, or pHs. And all the pHs is the pH your water would have if it were perfectly balanced. Now, this is where the real work happens, calculating that pH value. It all starts with a constant, 9.3, and then we adjust that number using 4 key factors from our water analysis, which we call A, B, C, and D.
So, what are these letters? Well, each one stands for a critical piece of the water quality puzzle. A comes from your total dissolved solids, or TDS. B is based on temperature. C is from your calcium hardness, and D is from your total alkalinity. You put them all together, and you get a complete picture of your water saturation state.
All right, enough theory. Let's make this real. We are going to walk through a practical example, step by step, using data from a real water sample. This is exactly what you'll be doing out in the field.
Okay, here's our data from a tap water analysis. We've got a measured pH of 8.0, the temperature is 25 degrees Celsius, our TDS is 500, calcium hardness is 250, and the alkalinity is 100 milligrams per liter. These 5 numbers are everything we need.
Now let's get our constants. You'll probably want a scientific calculator for this. First up, constant A for TDS. The formula is the log of your TDS minus 1, and then you divide that whole thing by 10. For our 500 TDS, that gives us 0.17. Next, constant B for temperature. That formula is negative 13.12 times the log of your Celsius temp plus 273. Then you add 34.55. With our 25 degrees, that works out to 2.08. Then we have constant C for calcium hardness. That's the log of your calcium hardness minus 0.4. For us, that's 2.0. And finally, the easiest one, constant D for alkalinity, is just the log of your alkalinity. The log of 100 is 2.0. Simple as that.
Okay, we've got all our pieces. Now we can solve for that pH of saturation. We just plug our numbers into the formula. That's 9.3 plus 0.17 plus 2.08 minus 2.0 plus 2.0. And that gives us a pHs of 7.6. And remember, this is not the water's actual pH, right? It's the theoretical pH it would have if it were perfectly balanced.
And now for the final easy step. We go back to that main formula. LSI equals actual pH minus our calculated pHs. So that's our measured pH of 8.0 minus the 7.6 we just figured out.
We did the math. We have our number. But what on earth does it actually mean? This is the moment of truth. This is where we translate that number into an actual verdict on our water system.
So our final LSI value for this water sample comes out to a positive 0.4. We got that by taking our actual pH of 8.0 and subtracting our saturation pH of 7.6. So what does a positive 0.4 tell us?
Well, here's how to read the results. Anything between negative 0.3 and positive 0.3 is generally considered okay. It's balanced. If your number is below negative 0.3, your water is corrosive. If it's above positive 0.3, it's scale forming. So our result of 0.4 is just a little bit outside that acceptable range on the positive side. That tells us our water has a slight tendency to form scale. It's a heads up that we might need to adjust our treatment to bring that number back down into balance.
And you really have to remember, this isn't just a math problem. This calculation is one of your best tools for being proactive. This is how you protect really expensive equipment, how you ensure water quality for the public, and how you truly master the craft of water treatment.
So now you have the tool to predict how your water is going to behave. And here's the thing, water is always going to seek its own balance. The real question for you, as the operator, is this: how are you going to guide it there?